There are four types of Fourier transforms you need to know about: the continuous time Fourier series, or CTFS, the continuous time Fourier transform, or CTFT, the discrete time Fourier transform, or DTFT, and the discrete Fourier transform, or DFT. The continuous time Fourier series is for signals that are periodic in time, and if they're periodic in time, that means that they're discrete in frequency. So in particular, if the period in time is t0, that is to say the signal repeats itself once every t0 seconds, then it only has energy at frequencies that are multiples of the fundamental frequency. That is to say, at frequencies that are multiples of omega naught, which is 2 pi over t0 radians per second. And what Fourier showed originally is something that we now call the inverse transform. He showed that any signal x of t that's periodic with a period of t0 seconds can be written as the infinite sum of cosines, and we're going to use complex exponentials instead of cosines. We'll say that it's the infinite sum of signals of the kind e to the jk omega naught t, which, as you know, is the cosine of k times omega naught t plus j times the sine of omega naught t. And we'll get the magnitude and phase of that sinusoid by multiplying it by some complex scalar, x sub k. X sub k is a complex number. It has some magnitude and some phase, and those tell us the magnitude and the phase of the corresponding cosine. And Fourier showed that any periodic signal can be represented as a summation of this kind. He also showed that we can get those Fourier series coefficients, the x sub k's, by something that we now call the forward transform. That is to say, by multiplying x of t times e to the negative jk omega naught t, the complex conjugate of e to the jk omega naught t, and integrating over any complete period, for example, from 0 to t0, or from negative t0 over 2 to positive t0 over 2, or any other complete period, and then normalizing, multiplying by 1 over t0. And one of the things that was demonstrated by Parseval, it was this thing that we now call Parseval's theorem. People sometimes say that this just is a demonstration that the Fourier transform is unitary. Unitary is a complex word that just means that the power is the same in both the time domain and the frequency domain. So we can calculate the power of the signal in the time domain by taking the magnitude of x of t squared and integrating over any complete period, and then dividing by the length of the period. So for example, we can integrate from 0 to t0 and then divide by t0, or we could integrate from negative t0 over 2 to t0 over 2 and divide by t0. And that gives us the power of the signal in the time domain. And what Parseval showed was that that's the same as the power in the frequency domain. That if we take the magnitude of the Fourier series coefficients and add them over all k, we get the total power in the frequency domain, which is the same as the power in the time domain. The continuous time Fourier transform is kind of like the Fourier series, except extended for signals that are not periodic, so extended to signals that are infinite in length. So the forward transform now is basically exactly the same form as the forward transform for the CTFS, but instead of integrating over a period, we're going to integrate for t equals minus infinity to infinity. And because it's infinite length in the time domain, it's therefore not discrete in the frequency domain. So the frequency variable is going to be a real number, capital omega. So we take x of t and multiply it by e to the negative j omega t, and integrate from minus infinity to infinity in the time domain to get x of j omega. The inverse transform now, because it's not discrete in the frequency domain, we have to integrate in the frequency domain. So the inverse transform is the integral from minus infinity to infinity d omega of x j omega times e to the j omega t. And now, because we didn't normalize in the time domain, we have to normalize in the inverse transform. We multiply by 1 over 2 pi. There's a version of Parseval's theorem that applies to the continuous time Fourier transform, but because it's infinite length in the time domain, it no longer makes any sense to talk about the power in the time domain, and so instead we talk about the total energy in the time domain. The total energy in the time domain is the integral from minus infinity to infinity of x of t squared magnitude. And that's equal to the total energy in the frequency domain, which is the integral from minus infinity to infinity of the magnitude of x of j omega quantity squared, integrated d omega, and now we have to normalize in the frequency domain since we didn't normalize in the time domain. So we multiply by 1 over 2 pi. The discrete time Fourier transform is applicable to signals that are sampled in the time domain, that is to say they're discrete in the time domain. That is to say that we only know the value of x of n at integer multiples of n, at the times x of 0 and x of 1 and x of 2 and so on. It doesn't have any defined values at all in between those integer sample times. And since it's discrete in the time domain, it's going to be periodic in the frequency domain. And likewise, since it's infinite in the time domain, it will be continuous in the frequency domain. So the forward transform is kind of like the CTFT, except instead of integrating over x of t, we have to add over x of n. We'll add from n equals minus infinity to infinity x of n times e to the negative j omega n, and that gives us x of e to the j omega. We'll use a little omega here to mean frequency in radians per sample, rather than frequency in radians per second. And because it's discrete in the time domain, it's periodic in the frequency domain. If we take little omega and add 2 pi to little omega, we get exactly the same value in that summation. And so it's periodic in the frequency domain with a period of 2 pi. We can't tell the difference between x of e to the j 0 and x of e to the j 2 pi. They're exactly the same thing. And so the inverse transform then will be the integral over any complete period in the frequency domain, for example from negative pi to pi, or from 0 to 2 pi, of x of e to the j omega times e to the j omega n integrated d omega. And again, because we didn't normalize in the forward transform, we have to normalize in the inverse transform. We multiply times 1 over 2 pi. There's a version of Parseval's theorem that applies, and it looks a lot like the CTFT Parseval's theorem. The total energy in the time domain, the sum from n equals minus infinity to infinity of the magnitude of x of n squared, is equal to the total energy in the frequency domain, which is 1 over 2 pi times the integral from 0 to 2 pi of the magnitude of x of e to the j omega squared integrated d omega. None of these things that I've talked about so far are actually of any use whatsoever if you want to do stuff on a computer. If you want to do stuff on a computer, you need something which is discrete in time and discrete in frequency, so that you can compute its samples in the time domain, and from those compute its samples in the frequency domain. If it's discrete in frequency, that means it's going to be periodic in the time domain. And if it's discrete in the time domain, that means it's going to be periodic in the frequency domain. And this is something that we call the discrete Fourier transform. The DFT is actually just a scaled discrete time Fourier series. So it's going to look a lot like the continuous time Fourier series, but scaled with the scaling factors that look more like a Fourier transform. So just like the CTFS, it has a fundamental frequency. We'll assume that the period is capital N samples, and usually this is just a made-up period. Usually that just means we'll take a signal, which is finite length, capital N samples long, and because it's finite length, we'll pretend that that's one period of a periodic signal. And so its imagined fundamental frequency is omega naught, which is 2 pi over capital N, radians per sample. And so we'll calculate a forward transform, which is like the DTFT, except that it's only over one period. It's the sum from little n equals 0 to capital N minus 1 of x of n times e to the minus jk little omega naught n. And notice now it's discrete in frequency because it only has energy at integer multiples of 2 pi over capital N. And so we call its DFT coefficients x of k. And I'll use the square brackets here to denote that this is a Fourier transform rather than a Fourier series, and that's just a scaling convention. That just means that we didn't normalize the forward transform. Instead, we're going to normalize the inverse transform, like we would for a Fourier transform rather than a Fourier series. And so the inverse transform is 1 over n, there's that scaling that I was just talking about, times the sum from k equals 0 to n minus 1 of x of k times e to the plus jk omega naught n. Parseval's theorem here, well, this is a Fourier transform rather than a Fourier series, so we'll compute the energy rather than the power. But the energy is only over a finite length. It's from the sum from little n equals 0 to n minus 1 of the magnitude of x of n squared, and that's equal to the total energy in the frequency domain. There are a lot of Fourier transforms and Fourier series that you can compute directly from these integral and summation formulas, and one of them that we'll do in the sample problems is the Fourier transform of an exponential. But there's one pair of transforms that are really kind of difficult to figure out on your own if you haven't seen them before. And so I'm going to spend a little bit of time at the end of this lecture right now talking about these two pairs of transforms. Those are the discrete time impulse and the continuous time impulse. The discrete time impulse is really just a convenience function. It's defined to be a signal which has a 1 at one particular sample, say n equals n naught, and a 0 everywhere else. And we'll call that delta of n minus n naught. So delta of n has a 1 at n equals 0, delta of n minus n naught has a 1 at n equals n naught. And this is useful primarily because it gives us a way of finding the value of any function at one particular sample. So it gives us an arbitrary black box, and this black box works as follows. Take that signal, f of n, and multiply it by a delayed impulse. Multiply it by delta of n minus n naught. And the result of that product, obviously, is non-zero only at n equals n naught. It's 0 everywhere else. And so if I add it from n equals minus infinity to infinity, I get just that one sample, f of n naught. This is an absurdly complicated procedure, obviously. This is not something that you would do if you just wanted to find the value of the function at one particular place. But this concept is useful because it allows us to talk about the dTFT of an impulse, and conversely, it allows us to talk about the DFT of a complex exponential. So the dTFT of an impulse is just delta of n minus n naught multiplied by e to the negative j omega n, and then added from minus infinity to infinity. And so we just get that e to the negative j omega n sampled at the time n equals n naught. So x of e to the j omega is this complex exponential. It's something which has a magnitude of 1.0 at every frequency, and its phase varies as a function of frequency. Its phase decreases linearly as we go up to higher and higher frequencies. This is actually kind of useful because it's something called an all-pass transform. It has a magnitude of 1 at every frequency. But it's also useful as a building block. So for example, if we want something that has a Fourier transform which is cosinusoidal, say it's a Fourier transform that has a peak at omega equals 0, and a trough at omega equals pi over d, and another peak at omega equals 2 pi over d, and so on, we can construct that by taking a pair of impulses, one at n equals plus d, and one at n equals minus d. And the Fourier transform of each of those is a complex exponential, so we'll multiply each of them by 1/2, and then we get 1/2 e to the negative j omega d plus 1/2 e to the positive j omega d, which is the cosine of omega d. All right, that's maybe not something that you need to do very often, but here's something that you need to do very often. You very often need to know what is the Fourier transform of a cosine. And it turns out that the only meaningful way to define this is in terms of impulses. If we have a cosine at the frequency 2 pi a over capital N, well, that's a pair of exponentials. That's e to the plus j 2 pi a little n over capital N, plus e to the minus j 2 pi little a times little n over capital N. And so its Fourier transform is an impulse at k equals a and an impulse at k equals n minus a, scaled as necessary in order to make them work in the inverse Fourier transform formula. All right, working with discrete time impulses is sometimes a little bit arbitrary because that discrete time impulse signal is just so obvious. The continuous time impulse signal is actually more useful, but more esoteric, right? If we want to do the same kind of thing that in continuous time that we did in discrete time, then we need to have something which is actually 0 everywhere except at t equals t naught, but it's infinite in amplitude at t equals t naught. And it's infinite in a very special way, right? There's lots of different kinds of infinity. It's infinite in the very special way such that if we integrate over any period on the time domain axis that includes t naught, the total integral is 1. And if we integrate over any other period on the time domain axis, the integral is 0. And if we define the signal in this way, then if we take that spike at t equals t naught and multiply it by any function f of t, and integrate, for example, from negative infinity to infinity, then we get f of t naught. So here's that black box that allows us to take just one sample of the signal f of t. This is actually the reason why Dirac invented the delta function. It's basically a way of taking continuous time and turning it into discrete time. So for example, if we want to find the Fourier transform of an impulse, well, we take that delta of t minus t naught and we multiply it by e to the negative j omega t, and we get a Fourier transform which is e to the negative j omega t naught. That is to say, it's an all-pass signal. It's a signal that has a magnitude of 1 at every frequency, and the only thing that differs as a function of frequency is its phase. This is useful as a building block. If we want a signal that has a Fourier transform which is a cosine, it has a peak at 0 and a trough at pi over d and another peak at 2 pi over d and so on. We can get that by taking a delta function at t equals plus d and a delta function at t equals minus d and scaling them both by a half and adding them together. And the Fourier transform of that thing is cosine of omega times d. And actually quite a bit more useful, if we have an infinite length cosine, this is a signal that has an infinite total energy, and so its total energy in the frequency domain will also be infinite. And in fact, its total energy in the frequency domain is infinite because it's composed of a pair of impulses. We take delta of omega minus alpha and delta of omega plus alpha, scale them each by a half, and then scale them each by 2 pi, because of the 1 over 2 pi in the inverse transform formula. We get the Fourier transform of cosine of alpha t is pi times the delta of omega minus alpha plus pi times delta of omega plus alpha. All right, these are the Fourier transforms that you need to know. You need to know how to compute the forward and inverse transforms for the Fourier series, the CTFT, the DTFT, and the discrete Fourier transform. And in particular, you need to know enough about impulses in order to be able to calculate the forward transform of an impulse and the inverse transform of an impulse, both in discrete time and discrete frequency, and in continuous time and in continuous frequency. That's all. Thanks.